Hello, my name is Thomas. I'm representing investmentexcel.com in this presentation of the basic building blocks of the Vasicek model, or perhaps more rightly, the Vasicek model dynamics. This model was built in 1977 and is one model out of many within the universe of stochastic interest rate models, particularly stochastic interest rate models based on just one short rate. Today we will only look at the stochastic dynamics and its distribution. We will not focus today at the application in terms of pricing with the Vasicek model. Please refer to other sessions where this is done. The video here and the Excel and the underlying VBA coding are all available on the investmentexcel.com site and the site spotify.com. Alright, let's just kick off by presenting some statistical features of the model. The Vasicek model, and ultimately the Vasicek model's ability to price interest rate contingent products, is based on this continuous stochastic differential equation. It tells that the change in the interest rate is governed by a mean reversion process defined here by the term A times B minus RT, and a volatility defined by sigma. The mean reversion process has the nice feature that the stochastic interest rate has a tendency to move towards a predefined mean reversion level, and this is the B. And the A is the speed or speed level at which this reversion occurs. It has one feature that is often criticized, and that is that the short rate can turn into negative territory, because the interest rate process here, the solution to the SDE, is a normal distribution, or the rate are drawn from a normal distribution. So in principle, the short rate at some point in time, some future point in time, can turn into negative territory. From this solution to the continuous stochastic equation, we can see that the expected level of the interest rate at some future time is defined independent of the rate at time t. So it has an unconditional mean, and it also has an unconditional variance. So it's very easy to implement it in a simulation by just drawing from a normal distribution described by these two moments, the mean and the variance. We see in both equations that there is no RT. We only have the known level of R0, which is the rate today when we initialize the process, and we have all the constants here, and the T is just the time period. So let's just try to simulate one stochastic path over 10 years with a quarter of a year a step, so 40 steps in total. We will use the following input for the model. 0.5 convergence, mean reversion level 4, volatility 10, and we kick off the process with a rate at 3%, today's rate. Note that the mean reversion level B is also the long-term value in the process. So if we assume that t goes to infinity, we will get a rate at 4%, and we can probably see this in this equation. If t goes to infinity, this expression goes to 0. If t goes to infinity, here this expression goes to 0, so we have left an expected value in the very, very long run at b, corresponding to the mean reversion. Alright, let's try. Let's see, in 4 periods at time 1, we draw a short rate from the normal distribution with an expected rate at this level, calculated from this equation, and here we have the variance calculated from the variance formula, the unconditional variance formula. So these are the moments describing entirely the normal distribution of short rates at that particular point of time. And now we'll try to simulate. So we have to draw or invert the normal distribution in order to get a rate. And the way we do that normally is using the norm inverse function, and we get Excel to choose a random probability in a CDF based on the 2 moments. And we do that for all 40 steps, leaving us with one entire path over the next 10 years. Let's see the dynamics when I activate the rand function in Excel on and off. That will give some dynamics. So here we have one path described here nicely. Perhaps we can see some kind of reversion towards the mean at 4%, so it never gets really out of sync. There is a physical constant pulling the universe towards the 4%. Okay, I will draw one more time, and here we have another sample, and so on. And we see, okay, except for that one, but otherwise the mean reversion can be seen. We could try to change the volatility somewhat, and also the convergence. So the lower I put the convergence, the slower the reversion will be towards the mean reversion level. So let's just try to put it at 0.25, and we see larger tops and lower bottoms, and we also see from this the negative yield. So here is basically the biggest drawback of the model. So despite all its nice features in terms of implementation and intuition, it has this problem of potentially giving negative rates in the future. Okay. So that's basically the way the Vasicek short rate model works. And perhaps I should just say that even though we call this a Vasicek process, originally it is not Vasicek's defined process, the SDE. The SDE is actually contribute to Ornstein and Ubanking. So theoretically speaking, this is an Ornstein-Ubanking process, but because it is used in the Vasicek modeling of interest rate products, it is associated with the Vasicek name. Anyway, so clearly with evolution of stochastic path of short rates, we will be able to price any product on the path, whether it's an option or non-callable bond, callable bond, or whether it's a zero coupon bond. And this is exactly what we'll see in another session. And this is also what Vasicek originally used his process for, was to calculate not just one zero coupon bond at one time, but the entire term structure at any given time in the future. So this is in short what the Vasicek article and the Vasicek dynamics here was all about, was to price zero coupon bonds. Alright, I will leave it with those words, and I will talk to you later. Bye bye.